Hello learners, welcome back to the course on deformation processing of materials. In the previous lectures, we saw some of the defects observed during the rolling operation, and towards the end, we saw some parameters which govern the rolling operation or which play important role during the rolling operation. In the end of the class, we had seen about maximum draft. So let us begin today's class with a numerical based on maximum draft. Okay. So we'll see a numerical example today. So suppose a rolling mill is functioning and cold rolling is being done. The rolling mill is doing cold rolling. Roll diameter is cold rolling in a mill. Roll diameter is given to us as roll diameter is 600 mm, and if the coefficient of friction between the rolls and workpiece is taken as 0.08, there are two cases here. So first case is mu is 0.08, and in the second case mu becomes 0.5. This is a hot rolling condition. Let me not call this as cold rolling. Simply let us say rolling in the mill. So these are the values, and suppose if a 300 mm thick slab is being reduced, 300 mm thick slab is being rolled. So we have to determine the maximum draft possible or maximum reduction possible in both of these cases. Find the maximum reduction. Okay, so let us see the solution. It will be very simple. In the previous lecture, we saw that the maximum draft or maximum reduction is given as Dmax, which is nothing but mu square r, where r is the roll radius. Okay. So let us call this equation 1. Here r will be nothing but half of the roll diameter. So it will be 600 by 2, that is 300 mm. Okay. Therefore, in the first case, Dmax will be mu square r, which is nothing but here mu is 0.08 square into r, which is 300. And upon calculation, we get this value as approximately 1.92 mm. Okay. So this is the maximum reduction possible. Now in the second case, when mu becomes 0.5, this maximum draft or maximum reduction will be again mu square r, which is nothing but 0.5 square times r, and this comes out to be approximately 75 mm. 75. So this was a numerical, and here we can see that if we increase the coefficient of friction between the rolls and workpiece, the amount of reduction or maximum reduction which is possible also gets increased, means we can reduce the slab to a more lower thickness. Okay, now let us see uh, one of the important concepts or thing related to the rolling operation. Okay. So now we will see the elastic and plastic curves for a rolling mill. Elastic, let me say this as characteristic elastic and plastic curves. So these are the characteristics of a rolling mill itself. Characteristics. Characteristic elastic and plastic curves for a rolling mill. So there will be always some resistance to the deformation when we try to deform the workpiece, even using the rolling mills or any other mechanism. If we try to deform, there will be some resistance offered to the deformation. So if the resistance is more, then there will be no deformation. So if resistance to deformation is more as compared to the applied pressure, there will be no deformation. No deformation. Suppose this is my workpiece, and if I try to deform it by application of some external load, then there will be some resistance which will be offered by material to the deformation. Resistance to deformation. Now, for any given condition of operation, the rolling load varies with the thickness of the workpiece, which is indicated by plastic curves and elastic curves. So the typical plastic and elastic curves are represented as let me change the color for so suppose this is my rolling load or rolling pressure, anything we can represent on this axis. So suppose this is rolling load, rolling load, and this is my sheet thickness. Then the typical plastic curve of the mill is represented as, let me use another color for this. So this will be something like this. Okay, this is the plastic curve. And also the elastic, there will be an elastic curve which will be correlating the elastic deformation of the rolls and workpiece. So the elastic curve will be something like this. Okay, so this is my elastic curve, elastic curve, and this is the plastic curve. Okay, so what this represents is, suppose we had an initial thickness h naught, and we try to reduce the thickness. So at these particular conditions, suppose I need to reduce the thickness to HF. So here the load P or pressure P will be required for this reduction. So this is indicated by this elastic and plastic curves. And this distance is nothing but the roll gap or separation between the rolls. So this is the roll gap. Roll gap. Okay. So this is a typical elastic and plastic curve, characteristic elastic and plastic curve representation for a rolling mill. Now, in case of actual rolling operation, suppose there is a breakdown of lubrication or the temperature decreases. In that case, the coefficient of friction will increase, and also there will be chances of increment in the flow stress. So in that case, this plastic curve gets shifted towards upper or right side, and which will lead to a final thickness or a thickness value which will be higher than the final thickness which is desired to us. So let me represent with some other curve what I am talking about. Let me copy this particular section, copy it, and again go to drawing board. And let me paste it here. So, paste it here. So this is the typical curve we were talking about. Now let me erase these portions. This was the initial roll gap. Okay. Now in this case, what will happen? This is my sheet thickness. Sheet thickness. Okay. Now if the coefficient of friction mu or the flow stress sigma increases, then in that case the plastic curve will shift towards the right side or upper side. Okay. So in that case This will be the condition. So what will happen here is, in case of, now let me call the final thickness as HF1. We wanted to go to HF1, but now this was, say, P1. Okay. Now in this case, what happens is, this particular elastic and plastic curves intersect now at, say, HF2. HF2. Okay. And this is HF1. Okay. Now, so here the plastic curve, this particular curve has shifted due to increase in the coefficient of friction or flow stress. Okay. Plastic curve shifted due to increase in mu or sigma. Okay. So now what will happen is, these curves will now intersect at this particular point, where the pressure is now E2. This was, say, E1. This is now E2. Okay. So what happens now is that we wanted to go to thickness HF1, but due to the increase in coefficient of friction or flow stress, we will be reaching only HF2. So this is not desired. Now, what we need to do in order to achieve HF1 in this particular case is that we need to shift the elastic curve toward left, so that again the intersection occurs at HF1. So that will appear like, say, this is HF1. So now the elastic curve will be something like this. Okay. So this means that in order to shift this elastic curve towards left, we need to reduce the roll gap, as it can be seen from here. This is the new roll gap that we need to maintain. New roll gap. Okay. And you can see that if we reduce the roll gap, the pressure automatically increases, and now it reaches P3, so that the thickness can be reduced till HF1. Okay, so this will be P3. This happens so as to get the final thickness of HF1. Okay, so this was the entire thing related to elastic and plastic curves. Let me write it down here also. So, okay. Now these were the points that the pressure increases or the load increases either due to increase in flow stress or the coefficient of friction. Okay. This increase was E2. The pressure increases due to increase in flow stress or that is coefficient of friction or coefficient of friction. And what happened here is that we now need to reduce the roll gap so as to increase the pressure to achieve the final thickness which is required. So here expected we expected here that we will get the thickness HF1. We expected to get the thickness HF1, but due to above reason we could get HF2 only. Thus, to further reduce the thickness, we need to reduce the okay. Okay, so this was the parameters or facts or everything related to ruling that we uh, discussed in the particular course. This does not include all the parameters and everything in detail, but this was a glimpse to the ruling process which is used for metal forming operation. Now, having completed the discussion on rolling operations, we will now begin the second metal forming process for this course. So now we will start our discussion on the extrusion process. Okay, so today we will begin the extrusion process. So let us begin our discussion on extrusion. So what is extrusion? Extrusion is also a metal forming process in which the metal is uh, allowed or is passed or forced to flow through an orifice by application of compressive stresses or loads so that it gets reduced in cross section. Okay, so this is nothing but this is also a metal working operation or metal forming operation, metal forming process. Forcing the billet or material or metal. Here initially, generally the initial workpiece is billet, which is further transformed to the useful states. Metal forming process, forcing the metal usually in form of billet to flow it through an orifice under high pressure okay, to so as to get the desired shape or reduced cross section to get the desired reduced uh, we should not say reduced always to get the desired shape okay. So this process is known as extrusion. We will see in a while through schematics how this working operation or metal forming operation is carried out. Okay, so basically what happens in extrusion is that due to high forces or when the metal is pressed through the dies, there will be high compressive stresses on the workpiece, which in turn will lead to the compression or flow of the material, which in turn further will lead to a lower tendency of cracking or reduced tendency of cracking and reduction in defects like this pores or blowholes, etc. So that also the improved strength, etc. are observed in the final form product. Okay, so the basically the reaction of forces of the container, we will see what is container and what is ram, etc. So reaction of the container and workpiece lead to high compressive stresses. Okay, so the compressive stresses which are effective in minimizing the defects. Stresses are capable of minimizing the defects, and this makes this process very broadly or very widely used process or sought process, which is generally seeked upon at various stages or various places for forming particular shapes. Okay, and this makes this process suitable for wide applications, suitable for a wide range of applications or products. Basically, we form the products out of these processes, and also this property here makes it possible to reduce the cross section or to form materials like stainless steels, etc., which are difficult to form by other processes, which may lead to fracture or failure of the components. Okay, so this enables forming of materials like stainless steels, and nickel alloys, etc. Nickel alloys, etc. So, like we had seen in rolling, extrusion is also broadly classified into hot working and cold working, that is hot extrusion and cold extrusion also. Okay, so if we see the if the forming operation is carried out above the recrystallization temperature, then this will be hot forming, and below the recrystallization temperature it will be cold forming. So above recrystallization temperature, the process is hot forming, and below the recrystallization temperature, this will be cold forming. Cold forming. Okay. Okay, and also generally shapes like circular cross section or rod like shapes, cylindrical tubes, or L-shaped cross sections, etc., are generally formed using this process. So general cross sections will be general cross sections will be like circular ones, rectangular or square ones, or some shapes like this. These are general shapes. Also, some complicated channels you would have seen of aluminum or pipes, etc., of different cross-sectional shapes are formed using the extrusion process. And also during this extrusion operation generally compressive and shear forces are dominating ones. So tensile forces are do not that much effective, or they do not play crucial roles here. Okay, so compressive and shear forces act. Compressive and shear forces play crucial roles. Crucial role. Okay. So these were some concepts, or means some points related to extrusion process. Now let us see the broad classification of this extrusion process. Okay, so the extrusion process is broadly classified into two categories, which is direct extrusion and indirect extrusion. So let us see what is direct and indirect extrusion. So let us see the classification of extrusion process. So at first, let us see what is direct extrusion. Direct extrusion. So in this process, basically the ram which is used to press or push the workpiece, and the final product which is the extrusion or extruded product. Extruded product is also known as extrusion directly. So the move direction of motion of ram and direction of motion of the extrusion are same in case of direct extrusion. Okay, so let us see through the schematic diagrams how these processes or these things appear. Okay, so as I mentioned earlier, there will be container and RAM, workpiece, die, etc. in this operation. So let us see the arrangements. So there will be a box containing the billet or workpiece, which will be known as container. So let us say this is the container. And it will contain the billet. Attached to the container, there will be dies. So this is the container, and this contains the billet. So this is the billet. This is the billet. Let me draw it more clearly. So this is the billet, and again to form the particular shape or desired shape, this there will be an orifice through which this metal or workpiece will flow. Okay. And finally, it will get transformed to the desired shapes, say like this. So the component required for this operation, which will lead to the deformation, will be dies. They are made of hard materials like die steel, etc. Okay. So dies will be like this. Here there will be dies. These are the dies, and to hold these dies, there will be die holders, which will be attached to the container. So let me draw the die holder also. So these will be attached to the container with die holders, and this is the extruded part which comes out finally after the extrusion process. This is the extruded part. Now to push this billet into this orifice, there will be a ram which will be uh, forcing a dummy block or some other material which will support this billet. So let me draw the dummy block and ram with some other color. So this is the dummy block, and attached to it will be the ram. Ram will basically this ram will press the material. This will push the billet to pass it through the orifice. So this is the ram, Now, upon application of force from here, this ram will press the material, and finally the billet will pass through the orifice and it will get reduced in cross section. Here, since we call this direct extrusion process, you can see that the direction of movement or motion of this ram and the extruded product are same. Okay. So this was the container. Let me label the diagram. Just use some other color for the labeling purpose. So this was the container. So this is container. This was RAM and this was the dummy block. Dummy block. This was the billet. Let me erase some part of the diagram itself to write billet here. This was the billet. And the part coming out is known as extrusion. This is extrusion. These are the dies and die holder. Die. This is die holder. Die holder. Okay. And this entire setup is for the direct extrusion process. Let me hit this. So this was the container. So this is the direct extrusion process where direction of this ram travel and extrusion are same. This figure is for direct extrusion. Okay. Here the direction of ram, let me write it down here. I've said it frequently. So here the direction of ram travel and direction of product are same. Okay. So this is the direct extrusion process. Now let us see the indirect extrusion process. Okay. So next thing is indirect extrusion. In this case, what happens is the direction of ram travel and the direction of extruded product or extrusion is the same. Okay, so let me draw the schematic so that it can be more clearly visualized. Okay, so it will be similar to this. Okay, let me draw it. So suppose we had the container. Here the shape of container will be somewhat different because it will be packed with some covering fluid. Okay. So say this is the container. Here is another one. Okay. And the billet is present over here. So this is my billet. Billet extended to the. Okay. So this is the billet and it will be supported by a closure plate which will prevent it from moving out of this container. So say this is the closure plate. Okay. So this is the closure plate which will prevent the billet from moving outwards. And again this billet will get extruded like this. This is the extrusion. Okay. And to cause this extrusion, there will be dies, as was the case in previous one also. So, say these are the dies, and these dies are now directly connected to the RAM, which is a sort of hollow RAM or cylindrical type of RAM with a hole in its center so that it can press the entire die, or individual dies even can be pressed by separate rams. So ram we had drawn with this color, I think, yes. So rams will be connected to this in this manner. So these will be the rams. So these rams will be pressed and ultimately the dies here, they will cause the material to flow through this orifice. Okay. So you can observe in this schematic clearly that the direction of ram travel and the direction of extruded part are opposite to each other. Here the extruded part moves in this particular direction. So this is the indirect extrusion. Here there will be almost negligible friction between the workpiece and the container because there is no motion, relative motion between the billet and the container, because as the ram presses the material, it the portion which is in contact gets reduced and there is no motion. Basically the material flows out from the orifice and gets converted into the desired shape. Okay. So let me write the names here again. This was the container. Again, this is the container. This is the billet. billet. This is extrusion. Extrusion. This is one of the rams. This is another ram, say, let us say. And this was the closure plate. The closure plate, which prevents the billet to move out of the container. Let me hatch it for clear visibility. This is the billet and extrusion. These were dies. Die. This. This is the die. Okay. And what is left out here? These rams may be hollow many times. We will write it later. Let me hash the container again. So this is the schematic for indirect extrusion process. Indirect extrusion. Okay. So we have seen the direct and indirect extrusion. Also, I had mentioned an important point here, which is no relative motion. No relative motion between the container and billet or workpiece. Workpiece or billet. Okay. So due to this region, the forces are also lower, and ultimately the power which is required for this extrusion process is also lower than that of the direct extrusion process. But this itself becomes a problem here, that this is the benefit that lower power is required, but ultimately to carry out this operation we will need complex rams, like hollow rams, and which will limit the maximum reduction in thickness, or the thickness which can be achieved through this particular operation. Okay, so frictional forces are lower. Thus, lower power is required as compared to the direct extrusion process. Okay, lower power required than direct extrusion. Direct extrusion. But the requirement of hollow ramps is a tedious, or means the disadvantage, not tedious, the disadvantage of this particular process. Requirement of complex ramps, hollow, usually hollow, usually hollow, becomes a disadvantage. Okay, so this was something related to indirect extrusion. Okay, so we have now seen what is extrusion and the broad classification of extrusion as direct and indirect extrusion process. Okay, and we have seen this schematically that how these processes are carried out, and these schematics also represent the entire extrusion process also. So basically, how extrusion is done. Okay, so we will end this class now. For today, we will stop here. Further, we will see some more parameters and things related to extrusion. Okay. Thank you, everyone.